Imagine walking past an ordinary wall, not knowing it is quietly harvesting energy from the same sunlight warming your skin. No panels, no spinning blades, no giant machines, just paint. It sounds like science fiction. But laboratories around the world are already trying to turn walls, glass, and coatings into energy systems. And if this works at scale, entire cities could stop being passive consumers and start acting like power plants. Because the next energy revolution may not sit on top of buildings. It may be painted directly onto them. Modern civilization runs on surfaces, but most of those surfaces do absolutely nothing. Millions of square meters of walls, facades, windows, tunnels, and industrial shells simply absorb heat, weather, and pollution. At the same time, our buildings demand enormous amounts of energy every single day. So engineers began asking a dangerous question: what if the skin of a building could do more than protect it? What if paint itself became functional? Not decorative, not protective, but productive. The idea did not begin with paint companies. It began with a limitation that solar energy has struggled with for decades. Conventional panels are powerful, but they are rigid, visible, heavy, and tied to specific installation geometry. That works on roofs, but cities have far more vertical area than rooftop area. So materials scientists started chasing a different dream: solar technology that could be coated, printed, sprayed, or laminated almost anywhere. That dream gave birth to a family of ideas now loosely grouped under one seductive phrase: solar paint. But here is the twist almost nobody tells you. There is not just one energy paint. There are several competing pathways trying to turn coatings into useful energy. One pathway tries to generate electricity directly from sunlight like a flexible solar skin. Another uses coated or embedded materials in glass to guide captured light toward photovoltaic edges. And another approach aims to use sunlight and moisture to produce hydrogen fuel instead of electricity. The most intuitive version is the one people imagine first: paint that behaves like a solar cell. This is where perovskites changed the conversation. Perovskite solar materials can be processed in ways that look much closer to coating and printing than traditional silicon manufacturing. That matters because once you can print energy materials, the factory starts to look less like a chip plant and more like an advanced materials line. Suddenly, walls, facades, and prefabricated panels enter the story. Even better, perovskites have reached efficiency levels that forced the entire solar industry to pay attention. In Celeb, the numbers climbed so fast that what looked impossible a few years earlier suddenly became a serious commercial discussion. That is when the fantasy of painted power stopped sounding ridiculous. But electricity-producing paint is not only about opaque walls. Some researchers are chasing transparent or translucent coatings that turn windows into silent solar harvesters, instead of converting all incoming light where it lands. These systems can redirect selected wavelengths toward solar cells hidden at the edges. That means the surface can remain partly see-through while still contributing energy. If mature enough, a skyscraper would no longer be wrapped in dead glass. It would be wrapped in a giant vertical collector. Then comes the strangest version of all. What if paint did not generate electricity directly? What if it generated fuel? Researchers linked to RMIT explored a solar paint concept designed to absorb moisture from air and use sunlight to help produce hydrogen. In cette vision, the wall is disconnected to wires. It becomes een system. That idea is still highly experimental, but it expands the meaning of what energy paint could become. Not just electricity on a wall, but chemistry on a wall. So how can a painted surface possibly make energy? At the heart of every version is one basic mission: capture energy from light before it disappears as heat. In electricity-focused coatings, light excites the material and frees charge carriers that must be separated and collected. That sounds simple, but the engineering is brutal. The coating must absorb enough light, transport charges fast enough, resist water, survive heat, tolerate oxygen, and stay attached for years. A beautiful coating that dies after a season is not an energy technology. It is a lab demo. That is why so much of the race is not about peak efficiency. It is about whether the coating can survive the real planet. And here is where the idea becomes explosive. A mediocre coating spread across a gigantic area can matter more than a perfect panel installed on a limited area. Scale changes the economics, the architecture, and the psychology of energy. Once energy generation merges with ordinary construction materials, the question stops being where to place the system. The question becomes why any new surface would remain passive. That is the real threat this technology poses to the old energy model. Not one more gadget, but a redesign of the built world itself. But this story is not a miracle. It is a materials war. Perovskite systems still face brutal questions about long-term stability, manufacturing consistency, barriers, and environmental exposure. Window-based harvesting systems face efficiency trade-offs because transparency and power rarely want the same thing. Hydrogen-generating paint concepts face their own mountain of problems. From materials performance to collection, storage, and system integration. Then there is the weather, and dirt, and repairs, and the brutal cost of making something that looks like paint behave like infrastructure. Even so, the first meaningful applications may arrive sooner than people expect. Not everywhere at once, but in places where conventional panels are awkward, heavy, ugly, or space-limited. Think facades on commercial towers, prefabricated cladding, industrial sheds, transport infrastructure, and high-value architectural glass. The earliest wins may come from coatings that do not try to do everything, but do one useful job very well. A facade coating that adds some power. A window layer that offsets part of a building's daytime load. A hydrogen-producing surface in a specialized industrial setting. This matters because the built environment is one of the largest energy stories on Earth. Every country has walls. Every growing city is adding more surfaces. And every square meter that can shift from passive material to active material changes the math of energy transition. That is why researchers, governments, and energy companies keep chasing this idea even when the engineering keeps fighting back. Because if walls can produce energy, then cities stop being the problem and start becoming part of the power solution. And that brings us back to the wall. The wall you ignored? The wall that looked empty. Sivalset one day may charge a building, feed a battery, or help make fuel from air and light. If that future arrives, the biggest energy machines on Earth may not look like machines at all. They may just look like paint.